Okay, so let's review thermodynamics. Thermodynamics really has two things at play. First is enthalpy, heat stuff, okay? And second is entropy, and that's the tendency towards disorder, okay? So first let's talk about enthalpy. So enthalpy is talking about heat. So as we're talking about heat, we're looking at bond dissociation energies first, okay? So this is the amount of energy that's required to break a bond. Basically, what you're looking at is the delta H naught of a reaction is the heat of the reaction, and this can be calculated from the delta H naught of things broken minus the delta H naught of things formed. Now, as you remember, that little dot means that it's under standard conditions. So 1 ATM in a standard state. And the change in is final minus initial. But basically, these delta H values, we can look those up. So you add together the number of bonds that are broken, you subtract from that the bonds that are formed, and that's where your delta H of reaction is. This is an easy thing to do with a chart. You have to have the chart, though. Nobody expects you to memorize that. At least I certainly don't. I don't have those memorized. There's no way that I would memorize those things. We have big, huge handbooks for that. Okay, but now if we look at these by a reaction progress diagram, if we look at the enthalpy on the left-hand side, what we see is that as a reaction starts, this is where reactants are, there's some type of transition state, and then we go to our product. There's two different things that we can look at here pretty easily. The first is the activation energy. That's the amount of energy it takes to convert from the reactants to the product side, okay? The second is the change on delta H, and if that is a negative value, then this is an exothermic reaction. If that goes through the same transition state or a different transition state, whatever it may be, I'm assuming this is a different reaction, and your delta H is positive, that is an endothermic reaction, which means it's taking on, or it's pulling in energy versus releasing it. So that's what a negative delta H means. That neither of those mean that the reaction will happen or not. It's just looking at what could happen, okay? The other side of that coin is entropy. So this is a measure of disorder of a given system. So this is the reason why I always say my house, my room, whatever it is meant to be a mess. Because when things are ordered, then that's going against entropy. We want to have things in more disorder. And so the universe has a tendency towards that. We define this as delta S, or change in entropy. When we say that the reaction increases in entropy, total entropy, we say that it is spontaneous. Now, that word you think means, oh, it happens right now. That does not mean right now. That just means that it happens. That could be in a million years. So just realize that when you hear a chemist say spontaneous, it does not mean right now, okay? Delta S total is that of the system and the surroundings. The system's easier to kind of look at, so that's what I want to look at first. Sometimes the surroundings is a little bit more difficult. But basically, that makes sense. We've got total entropy change that happens within the reaction itself, and then, what's going on in the surroundings. So there's a lot to consider. So we might want to consider like combining two things. That would be a delta S that's negative. So in other words, you're going against entropy there. When it comes to delta S, you want this to be positive in order to increase entropy, okay? If we take a cyclic compound and we free it from its cyclic capabilities right there, that would be more disorder, because that compound can now rotate in many different ways, and so delta S in this case would be negative. I said that would be negative. It is supposed to be positive. So my apologies there. That is a correction. That would be positive. Okay, there we go. Delta S of surroundings can be negative if H is negative or various other reasons, and we'll just leave it at that for now. Okay. Next, we need to consider Gibbs free energy, which I think you're probably familiar with from general chemistry. So remember, if delta G is negative, then that means the reaction is favorable. In other words, it will happen. Doesn't reflect time again, even if we call it spontaneous, okay? Delta G is given by an equation, and that is delta H minus T delta S, excuse me, where T is temperature, okay? So free energy is another thing that we can do that looks very much like the enthalpy reactions that we were looking at before. It's just that we're going to name things a little bit differently. So if we have a negative delta G here, we call that exergonic process. In other words, the reaction will happen. It is a spontaneous reaction. If delta G is positive, then it's an endergonic process and it is not spontaneous. So it's harder to get that reaction to go. It's not likely to happen very easily. Okay, it's probably not going to happen. So that's what we're looking at when we're testing these. Well, reactions can happen at equilibrium as well. So if you recall, KEQ is the concentration of products over reactants. So if this KEQ is large, we can also relate this to delta G as being something that will favor products. So if KEQ is large, this negative will take place, and that means that delta G will be negative and the reaction will occur. So that's sort of what those two are related to as in this equation. So where R is the gas constant and T here again is temperature. Okay. So we have to consider both thermodynamics as well as kinetics when we're looking at a reaction and trying to figure out if it's going to happen or not. Well, I'll show you why in a minute, but let's review some kinetics as well. So when it comes to kinetics, what we're looking at is the reaction rate. So remember, rate is some constant K times the concentration of reactants. This has nothing to do with products. It has to do with what we're starting with. So if you've got a reaction where X plus Y equals Z, it has nothing to do with Z. It has something to do with X and Y. So the rate is equal to a K, some type of constant, times a concentration of X and Y. Now it could be that those are 0. It could be that they're 1. Or they could be 2 or 3. So all in all, if you have one compound that is coming together in the transition state, we would call that first order, okay? If we have 2 compounds that are coming together, then we're going to call that second order. And it can be 2 of the same thing, or it can be 2 of 2 different things. 3 compounds makes third order, et cetera, et cetera. Honestly, usually we don't have beyond a second order rate reaction because the likelihood of 3 things or more coming together for a transition state is relatively low. So that doesn't happen very often. So the transition state is what is going to determine the speed of the reaction. And in a minute, I'm going to show you something with multiple transition states. The reality is that the transition state that has the highest energy is what we're talking about as the transition state. That's the one that really counts. That's the rate limiting step, if you recall that term. Okay, so what is going to affect the rate constant and how can we speed that up? Well, remember, large K means fast reaction. That's going to make the rate go up. Activation energy is the first thing that I think of, right? How high is that hump that we have to go over? If the transition state requires a large activation energy, it's going to be a slower reaction. For example, you may know that diamond is constantly turning into graphite, and it is thermodynamically favored, but it has a huge transition state. Okay, there's a little hump up there at the top. I meant to make that more rounded. So this activation energy means that the reaction is very, very slow. So though they say a diamond's forever, it's not. It's a few millennia though, so you're probably going to think of it as being forever. So catalysts and enzymes are going to lower that activation energy. So if you have something that's a large energy hump, maybe they lower it to this. And it might have more than one hump there at that point, but that's still going to lower the overall activation energy. Temperature affects things. If we have greater heat, then it's easier to overcome that activation energy barrier. I believe in general, if you heat things up 10 degrees higher, that will roughly double your reaction speed. There's also steric effects to consider, so we have to get the transition state into an orientation that's correct, and some molecules, you just can't rotate them into the place that they need to be, and so that can certainly affect your reaction rate very quickly as well. Okay, so what does this stuff mean? Let's talk about combining these things, okay? So we're going to have to take this page kind of slow. When we have potential energy on the left-hand side, and our reaction rate is right here, there's two things we consider. We consider the activation energy, which we just talked about. That is what is dictated by kinetics, okay? So you lower the activation energy, the reaction happens more easily. You make a higher activation energy, it happens more slowly. So that's what we talk about when we talk about controlling a reaction kinetically, or a reaction that's under kinetic control. Okay? On the other hand, if we have a delta G here, so this amount of energy that is released in that reaction, that means that this reaction would be controlled by thermodynamics. Well, in this case, there's thermodynamics and kinetics that are at play, because I'm just giving you one example here. But thermodynamics is basically how much energy is released in the process of that reaction happening. So if a reaction is controlled by the fact that you've got more energy released, then it would be considered to be thermodynamically controlled. Okay? Sometimes the two are going to agree with one another. Sometimes they do not. And you can influence a reaction to give you one product or the other. So let's look at these two examples. Let's first consider the one on the left. Here I have A and B coming together. And we know that product 2 is lower overall energy, which means that the delta G here is quite substantial. So that's what delta G is going to look like. The activation energy for this one is smaller than what we would have for the other one. So what that tells me is that I'm going to get product 2. It is both kinetically and thermodynamically favorable. Okay, so that's going to be the case that we're going to end up with both of those as our final product. So we're going to get product 2. Okay. Now when that happens in the one on the right, we have two different scenarios here. So the first thing that I want to point out is that this is not as much of a high activation energy as this one. So in the purple line, we have a higher activation energy. In the blue line, we have a lower activation energy. Okay, so that's the first thing to look at. But we also have to consider delta G. Well, delta G is about here for product 4, and it's all the way down here for product 5. That's the purple line. So that means that product 4 is going to have a smaller delta G, and product 3 is going to have a larger delta G. Here's what that translates to, you all. When we're looking at product 4, This is going to have a lower activation energy, but overall it's going to be higher energy. The products are higher in energy. So that is going to be something that is kinetically favored. On the other hand, when you go through this route to get to product 4, it's a higher activation energy, but the overall product is lower energy. We would say that that is thermodynamically favored. And that way, what we can do is we can control this and be able to get one versus the other. So these can sometimes be really good, but you have to think your way through them. When we're looking at a more complex reaction coordinate diagram, we have more than one hump on this one. So I want to make sure that you know what these things mean. Every hump that you go over, that is a transition state. So each of these is its own transition state. And that means that we have intermediates. So we have this intermediate here that's B, and this intermediate here that's C. So if you're looking at a mechanism, every time you have a hump, that means that we've got an arrow. So you're going to the next thing, and we have two intermediates. So what this is showing is that when we go on this little roller coaster here, we start off with A. So we're going to start with A. We go through the transition state between A, and as we go down, that enters B. So now we have B. Then we go on up through another transition state until we hit C. And so that's where we get C from. We go up above again and through another transition state before we get to our product, and that's where the product is coming from, okay? So this is something we're going to use as we enter mechanisms, and I'm sure that you're going to love that as much as me. I'm looking forward to it.